Everyone, we can go ahead and get started. So welcome back to Cyber Academy Week 5. Hope y'all's midterms, if they haven't already happened, are going well. Just some announcements. So next week on Friday at 6 p.m., we will be doing the Cyber ICPC Run Social. So we will be heading to Sawtell. We'll have two groups. One group will take the bus. One group will run there. The run takes 30-40 minutes or so, and it's like downhill to flat, so it's not that bad, trust. But if you would like to bus, there will be a group taking the bus. If you do plan to take the bus either on the way there or the way back or both, just make sure you do not forget your tap card. The CS department spring 2025 town hall will be in 3 weeks on Thursday. So this is a great opportunity for y'all to give feedback to the CS department. If you haven't done this before, if you have done this before, the form looks pretty much identical. But if you haven't, there's a form that you can fill out by, I think, end of next week. And it just asks questions like, what classes did you enjoy? What classes would you like changed? Is there anything else you'd like? You should say, more cybersecurity classes and professors. But there's also a separate town hall itself where the CS department will address the concerns directly in person. They bring in all the professors. They bring in like members of counseling and faculty or staff, and they just like announce changes, address concerns, etc. So definitely show up. If you do show up for the town hall, dinner is provided.
Yeah, okay. So we announced at lab and maybe a week back that PBR would be doing BIOS CTF this weekend. Unfortunately, BIOS decided to postpone it. So SAG, no meeting, no PBR meeting this weekend.
And there's no alternative CTF at the same time. So
yeah. So yeah, use that time to study for midterms, I guess. Don't die. Take it easy. All right. And then, of course, next week, we'll have Cyber Lab and Cyber Academy as usual. For Cyber Lab, we'll have a guest talk on DevSecOps from Nasir. And for Cyber Academy, we'll have a talk on coding theory by Arnav. And of course, Cyber Basketball Friday, as always. Yeah, and without further, let's hand it off to Eddie for his talk on quantum cryptography.
All right, quick thing. Anyone here know anything about linear algebra and know anything about direct notation? Raise your hand. Good job, Daniel. You guys know what RSA is, right? Okay, so basically, it's like the common encryption used in like all the networks, everything. It's used in everything. And basically, the problem is people can't break it because the whole process involves multiplying two large primes. And in order to encrypt, or more specifically decrypt the messages, you need to like factor that large prime number. But that's like super duper hard. Look at that O time. Look at that. It's too much. It can't be done. Thousands of years on the most modern supercomputers. That's how long it'll take. So basically, invincible. All right, let's imagine you're the president in 2077. I'm the president. I'm gonna pretend I'm the president. And the ops are after me. They found the word skivity has been outlawed in the country, and they found out that I said skivity in Discord in 2025. And they're after me. It's over. But quantum computers, they broke the RSA. They found all the instances that said skivity, and I'm cooked. I'm cooked, guys. How could this be? What could break RSA, guys? It's Shor's algorithm. All right. So our objective is to factor the prime number n, and we're going to recover p and q. All right. So first, we're going to choose a random number a and assume that the greatest common denominator between n and a is 1. If like it's not the case, then the thing's just going to repeat until it finds a that's 1. That greatest common denominator is 1. And then we need to find a period. So we're going to find a function f of x equals a of x mod n, and then it's periodic. We got to determine a of r is equal to 1 mod n. And then we're going to initialize, two 0 states, two qubit registers, apply the Hadamard transform, normalize all the states, blah, blah, blah. What is this? What am I doing here? All right. What's a Hadamard transform? Does anyone know? That's cooked. Okay. Do you even realize that the between the two zeros is supposed to be a tensor product and it's just implied and no one tells you this? All right, guys, that's a great question, like I just said. The answer is quantum mechanics. All right, guys, information is physical, okay? Everything in your computer, all the bits, they go through physical circuits and channels, but quantum physics takes it to a new level. Now you have physical information. The bits is now representing the literal momentum of particles, okay? So like practically everything you're gonna see here is theory, but in real life, they just have like some chip with like a bunch of particles. It could be thorium, cesium, one of those big guys, because they have special hyperfine states. We're not gonna get into that. And they shine lasers on them to make them do funny things. Spin up, spin down, right? So let's do some linear algebra. All right, guys. Who knows about direct notation? Like that. Oh, no, I just said that. No one knew. All right, guys. What would happen?
There's more chalk on right underneath. Like if you want a nicer one, like along the.
That's okay. All right, guys. I'm gonna find this. This is the worst chalk ever. It's so chalky.
Crazy hard.
I'm gonna make it even smaller. Okay, guys. What if I wanted to find this? Quite simply, transpose complex conjugate. This is also known as Hermitian. So you could say like, you could say this, the dagger, right? So what would be this, guys? Come on. What would this be actually? What is the answer? Come on. This is. Someone raise your hand. Arnav. That's so true, Arnav. 1-0. All right. What if I did this? What if I took 0, 0? This is an inner product. What happens if I did this? Daniel. It's yeah. So true. Or it's actually 1. I'm stupid. All right, and if I did that, what does this mean? I put 2 lines and a squared by it. It's still gonna be 1, obviously. Lines and a square. What does that mean? What does that do? Modulus squared, because each wave function is in the C2 plane. And if you do this, it produces a probability. This is Born's rule. Okay, keep this in mind for the rest of the talk. All right, also, I put a little operator there. Guys, this is what? It starts with eigen. It's an eigen value eigenfunction problem. Look, I put an operator on a state and I recovered an eigenvalue. Why is that? It's because it's a matrix. What am I doing here? When I apply an operator on a state, it starts with matrix and ends with multiplication. Okay? It's matrix multiplication. Quick challenge for you. See the matrix on there? Sigma Z. How would I represent each term as an inner product of sigma Z? How would we do that? Any ideas? Daniel? You should. Come on, Daniel. It's that. Okay, we're going to take detour on phase. Anyone see those 2 equations there? Guys, remember first order linear diffie-qs? Can you tell me what would happen? How can I rewrite H hat, the Hamiltonian operator on the psi wave function? What can I write that as? As adhering to, how do I make the time-dependent wave function? That's my question. Any ideas? Daniel? Guys, does that make sense? You just treat the psi as like some function, and then you do the math. You like divide, like you just set the time dependent part to the e, and then you solve. Right, guys? You guys get it.
Sure.
The extent traveled along the wave. So remember Born's rule? If I applied Born's rule, the probabilities would vanish, right? Because I defined this, the complex exponential, so it's going to turn the I negative by to I. So when you multiply, it's not there. So that phase vanishes when you find a probability. And this is an example of a single qubit. I'm gonna pull out the block sphere like this, friend. Single qubit can represent a block sphere. So this state would be, this is like positive x. It's like this, some angle theta. And okay, that's a theta. It's like been rotated along that axis. Yeah, it's a phase. It's around travel around the block sphere. It's another way you can describe it. Anyway, Hadamard gates generate superposition. Remember, it's the word I said earlier. So you take the Hadamard gate, apply it on a 0, makes a superposition. You apply it again, and it's back to 0 because Hadamard is a Hermitian operator. So its Hermitian conjugate is equal to itself. How cool is that? And then, like I said, those two zeros, there's actually a tensor product in them. What I mean by tensor product, I did 0, tensor 0. Remember that definition there. It's going to be like 1, 0, 0, 0, 0. Actually, take it with less. Here you go. Not that. That's good. Right. So cool. So that's how we define a 2-qubit register, and that's what we're going to be working with. Also, why is this not entanglement? Does anyone know? Daniel. I have such high hopes for you. It's not entanglement because I can represent it as a tensor product. There's a really cool thing called Schmidt decomposition. It's like if you have to add two terms of tensor products in order to define it, and there's some entanglement there, okay? But in this case, I wouldn't have to. All right, so it's not entanglement. All right, let's continue with yours. So let me give you a visual representation of what's happening. Okay, look over here. So it's like I've defined each x. You see the x there? That's just all your your bits, all your numbers, and they've all been defined equal superposition. So it's like this, continuing to infinity. This is their probability, by the way, their probability, and this is all your x's. Okay, so I've defined them in that way such that each state, so each bit string is equally likely. Okay, and we got this by applying the Hadamard, like by how many times we have like bit strings, pretty much. Then we're gonna apply this unitary. This unitary, don't worry about what it does, but what it does is that it fills the second register with the f of x function earlier, which is like the a of x, right? It's that periodic function. Okay, it's called like modular exponentiation. This is like the thing that makes up most of the processing for this entire computation. It basically just multiplies. It's like if I had a of x, like a of 2x0, like times like a of, it's like all the bits of the, it's gonna be like a of 2x1. It's like decomposing the binary. Yeah, okay. All right, and then you measure the second qubit register and you get this. What did this do? You're basically just isolated all the parts that follow your little thing, your little period. R. Okay. And then you apply quantum Fourier transform. Do people know what a Fourier transform is? Fourier transform. Okay, what does a Fourier transform do from what you remember? Arnav. That's true. It's the same deal here, except the frequency domain is like a frequency of qubits, and it's supposed to represent the constructive interference caused by this like periodicity. So basically, when you apply this Fourier transform, it's going to amplify all the probabilities like that. Okay? Make sense? Okay? You see the thing in the parentheses on the second line? So everything outside that parentheses, physicists like to call irrelevant. All right? It's irrelevant. It's a quantum phase. It's like almost like it's just this noise that's so permeated in your system that it's just, you might as well ignore it. It's just everywhere. So just remove it. No one cares. Okay? What matters is everything in that sum. Okay? And that sum is a geometric finite sum, and it can be computed. Because when you run this algorithm, you find its amplitude P and the corresponding frequency domain qubit register where the constructive interference coalesces. Okay, guys? So you can find the qubit register. You know what Q is because you know how many qubits you're dealing with, and you know what S is because you can compute it. What does that mean, you guys? Look at the fraction. It means you can solve for R, guys. It means you can solve for R such that this is true, and then you can decompose it. You can split the factor. And if you take the greatest common denominator of that, N, you're going to recover P or Q, guys. You're going to factor N, guys. And if you factor n, then you break RSA. Simple. Simple, you guys. And also this process would have to repeat if r is odd, because then it would give you like -1. So it will literally just repeat this process until it gets an r that is a even number. And then once you do that, you get p or q. And then you can solve everything. RSA is cooked. And the polynomial times O of log or log n cubed. That's pretty good. Hello, Arnav.
Wait, never mind. I just...
Okay. And this is the full quantum circuit picture. You can see they're doing modular exponent, and then they do the QFT. How can I prevent this theft though, guys? Like, all my stuff's being stolen now by Shor's algorithm. How do I save my presidency? That's another great question. More quantum mechanics. It's the BB84 quantum key distribution protocol. So we're going to transmit photons one at a time in a fiber optic cable. So generally information is sent in quantum bit string form. So there's like 2 different bit strings. You have your A bit string, which is your information, and your B bit string, which is going to be your basis. I'll explain that later, like a linear algebra basis, guys, because we can represent the same state in different bases. More specifically, I will show the example. This is like in the sigma z basis. I'm going to show you what I call the diagonal basis, which is a sigma x basis. You're not expected to know what that means. It's just special. And we're going to do that using density matrices. Who knows what a density matrix is? Daniel? You were telling me how much you do. Yeah, you use operators. Daniel is among the ignorant. All right, so we got BB84 in action. We got our little guy. He's sending a qubit 1, but he actually means skibbity. It's just special slang. He wants to send skibbity. He's sending a bit. I have 2 bit strings, the message and the basis, and I want to send bit 1 in the diagonal basis. It's the diagonal basis. Look at that. It's a diagonal basis representing 1 specifically, because 1 we're going to call the down, and 0 we're going to call the up. All right, and I'm going to denote the down by the minus, the plus, the up. Right. We're going to take the density matrix out. We got that answer. My bit goes through a quantum channel E. I'll define that a little bit. Unaltered, my friend measures a basis of the bit string number, in this case, either m minus or m plus, because he knows how long the bit string is, which is 1. So he's going to choose the appropriate base. And if he measures using one of these, he announces to me that he's received the message, and we correct errors, aka if he chose the plus basis. It's the basis of the BB84 protocol. So it's almost like you send your message, and it's completely private until you receive your stuff, and then you announce whether among each other if you actually receive the correct message. All right. And the probability that my friend gets 1 is the trace of the m minus. That's an identity. I'm basically doing an expectation value using a density matrix, Daniel. All right. Okay. But we are intercepted. An evil goon has intercepted my Discord message, but they don't have the correct basis. He operates on a quantum channel with a non-diagonal basis. So E0 and E1 I've defined as the inner product of the 0 and the 1 states, as per the top left corner. And if we take we use that definition of the quantum channel on our density matrix that we started with, representing our correct diagonal basis, you will notice he gets 1/2 times the identity. All right. That basically means that the part of the density matrix you should know that the diagonals represent probabilities. So the probability that he gets the wrong answer is 50%. So it's completely random now, whether he gets the correct answer or the wrong answer, this evil goon. Okay. And they say that this state is mixed. That's the physicist way of saying it. And if you're on the receiving end of this and you get like this nonsense, this random nonsense, you'll be able to detect the error increase. So you know that your channel has been compromised. How crazy is that? You'll know you're cooked. But in theory, the goon can be lucky and get the correct answer because it's 50-50. You could abort the process if the error has been exceeded, but there's also different types of protocols. So you can deploy decoy states. So you can like scramble the information and like increase the uncertainty. Uncertainty is a big thing, by the way. Quantum states, nothing is finite. Everything's probabilistic. I'm assuming everything up here was perfect, by the way. Usually it's not. You can do bit value pairing, but the one that's most likely to be used, should quantum computers become feasible, which I will explain in a bit, it's the E91. So actual entanglement requires that it satisfies Bell's inequality. If there's any sort of measurement along that quantum teleportation circuit, everything gets cooked. You could measure that it's exceeding Bell's inequality and you know immediately someone. And it's like a lot better because the information that will be taken, if there's such a measurement, will also be nonsense most of the time. Like probabilistically, I could show it, but it would take like an hour. But the probability they get it, like the correct information, is like quite low. Okay. And then also, why in 2077? Why would I say that quantum computers are out in 2077? President Me in the future would be safe and sound with protocols like BBA4 and E91 around. When I make day, is RSA going to die tomorrow? Probably not. RSA is going to be fine for at least the next 5 to 20 years, mostly because practical quantum computing is just not possible yet. Basically, they're having a crisis of scalability versus accuracy, because once you reach this subatomic scale, like you do in quantum mechanics, there's something called the uncertainty principle. Who's heard of this? Yeah, uncertainty principle. It messes everything up. It messes up your measurements such that it's always off by like some 10 to the 1 at the very least. Okay. And there's another thing called quantum error correction, which is usually most of the computation. Most modern quantum computation, 90% of it is just quantum error correction. And that stuff basically reduced it to about, I think the most modern models have 10 to the -4 error, or they call it fidelity because it's error in the frequency space, because it's funny. Okay. But we need 10 to the -10 to be realistic. So that's why people are struggling. Everything I just told you, in theory, should work. They just haven't tested it because they can't. All right. And yeah, that is my talk.
Anyone have any questions before we move on?
Everybody's brain is a little fried.
Yeah, I agree. But yes, thank you for that talk.
I was very privileged.
Yes. We'll go ahead and split into our 3 groups as per usual. Web up here in the front, reverse engineering on the left side of the room, and cryptography kind of on the right side of the room.